Now that you have an understanding of blockchain technology and decentralized applications, let's dive into decentralized finance, also known as DeFi. DeFi refers to financial applications built on decentralized networks. The main goal of DeFi is to transform traditional financial products into trustless and transparent protocols. Instead of relying on intermediaries like banks or brokers, DeFi apps allow you to directly interact with financial services through smart contracts, which are automated agreements encoded on the blockchain that autonomously execute and manage the terms of a contract when specified conditions are met. This automation not only minimizes human error, but also eliminates the need for trust between parties. This also allows users to gain control over their assets with the ability to manage and transact their funds securely and transparently anywhere in the world at any time. The direct interaction enabled by smart contracts in DeFi extends to a variety of services, such as borrowing, lending, and trading. Unlike traditional financial systems, there are no office hours for DeFi platforms. They operate 24/7, providing constant access no matter the user's location or time zone. This round-the-clock availability ensures that financial operations can proceed without delay, catering to the needs of an increasingly interconnected and globalized world. Another benefit of DeFi is the reduction of operational cost associated with financial transactions. By cutting out intermediaries, transaction fees are typically lower than those in the conventional banking sector. This democratizes access to financial services, particularly benefiting those in underbanked regions or individuals facing financial exclusion. It also creates a more competitive financial environment where innovation thrives, leading to better services and products for users worldwide. Some key examples of DeFi include decentralized exchanges, stablecoins, and lending protocols. Decentralized exchanges allow trustless swapping of cryptocurrency tokens. There are two main types of decentralized exchanges: an automated market maker and an order book. Order books require matching buyers and sellers, while an AMM uses pooled liquidity that trades algorithmically against your order without needing immediate counterparty matches. Stablecoins bring price stability to crypto. They peg their value to assets like the US dollar. This avoids volatility, which improves DeFi usability. And decentralized lending platforms allow users to lend and borrow cryptocurrencies from pools of aggregated liquidity. The interest rates are algorithmically determined based on supply and demand. Beyond these examples, there are several other types of DeFi applications that exist today. And with the code-driven open source nature of DeFi, the innovation will continue. Now that we've learned about DeFi, let's dive a bit deeper and build out a lending protocol. In the traditional financial system, lending involves banks or financial institutions providing loans to individuals or businesses. In return, the lender receives interest payments over time. This system plays a crucial role in the economy by offering liquidity and enabling capital growth. However, it's heavily regulated and often requires intermediaries, which can introduce inefficiencies and exclusivity. Now, let's contrast that with decentralized lending protocols. These protocols function on a blockchain network and are designed to be permissionless, meaning they're open to anyone, anywhere, without the need for a centralized authority or intermediary. Here's how it works. Anyone with digital assets can lend them out to earn interest. Conversely, anyone needing a specific asset can borrow it by providing other assets as collateral. This system democratizes access to capital and expands financial inclusion. The backbone of decentralized lending is smart contracts. These are self-executing contracts with the terms of the agreement written directly in the lines of code. They autonomously manage the custody of assets, calculate interest rates based on the supply and demand, and ensure that loans are adequately collateralized. Lenders contribute their assets to liquidity pools from which borrowers can take loans. This pooling mechanism spreads out risk and facilitates better liquidity management compared to traditional individual lending agreements. For lenders, this setup provides an opportunity to earn passive income on their assets without engaging in active trading or investment. For borrowers, it offers quick access to capital without the need for credit checks or the bureaucratic hurdles typically involved in traditional banking. Lending is not just a feature, but a fundamental pillar of the DeFi ecosystem. It not only frees up the capital locked in cryptocurrencies, but also creates opportunities for leverage in other financial activities within DeFi, enhancing the overall utility of the crypto markets. In our tutorial, we'll build out a lending protocol on Solana from the ground up. You will learn how to create smart contracts that will allow lenders to supply tokens to lending pools and earn interest, while borrowers can secure loans by collateralizing their digital assets. Let's get started. Let's get started building out our lending protocol. This will be a very simplified lending protocol of just two assets. We'll have SOL and USDC. A user will be able to deposit and withdraw, borrow and repay assets on the lending protocol. In a lending protocol, to be able to borrow assets, we're going to make the accounts over-collateralized. And to do this, we're going to have to calculate the health factor of the account, which allows an account susceptible to liquidation. If the account falls below the health factor, then it will be able to be liquidated. So overall, the main instructions that we're going to need here is depositing, withdraw, borrow, repay, and liquidate. And we're also going to need to set up the accounts that we'll need. So the main accounts that we're going to need is a bank for each asset that we want on the lending protocol and user accounts. So let's get started. We'll first set up our Anchor environment and then work from there. We'll navigate into our terminal. And we're going to use Anchor and init to set up the workspace that we're going to need for our Anchor program. Okay, and then we'll just cd to our new workspace and open that in VS Code. Okay, so now our workspace has been created. We're going to navigate into Programs, Lending Source, LibRS. And this is the basic layout for our Anchor program that's been generated from Anchor init. Let's first get rid of the instruction that was generated and the derive accounts and just have the basic layout for lending. Now, because this program is going to have a lot of different instructions with a lot of different accounts, we're going to separate things into their own folders and then pull them into the librs just for easy readability. So let's get started by first defining our state. And we're going to want to define what accounts need to hold state for this program. In source, let's create a new file and we'll do state.rs. And now, right off the bat, we should remember to create our mod files to be able to incorporate all of the separate files that we're making. So first in librs, we want to make sure we're going to use our state. So we'll just do mod state. Okay. And we'll go back to our state. And then we want to use Anchor. And then state is stored in the account. So we're going to use the account attribute to declare that this is a Solana account. And then because an account is going to take up space on chain, we're going to use init space to be able to calculate the space throughout our program. Okay. And then let's see, what's the first account that we want? Well, we're going to need accounts for the user. So let's create the user account. So pub struct user. And let's figure out what we want to save as far as user information. So we want to know who the owner of this user account is, and we're going to be able to initialize multiple user accounts for any user that comes to this application. So we'll do pub owner, and that'll be a public key. Now we're going to want to keep track of how much SOL has been deposited or borrowed, how much USDC has been deposited or borrowed, and then we're also going to want to keep track of the shares. And the shares are what we're going to use for interest calculations, which we'll get into as we need to calculate interest in the logic for the instructions. So let's first start out with the deposited SOL. Now, one challenge, if you're looking to amplify this program, is how would you update this for multi-assets, more than just two, for a lending protocol, since most lending protocols allow for more than just two assets. So what would be the best way to store this in the state and to manage all of the assets? Because this is not going to be the most optimal by just explicitly stating each asset in the struct. So now we'll keep track of the SOL shares. And then we'll need the borrowed SOL. And then the borrowed SOL shares. We'll need the deposited USDC. The deposited USDC shares, the borrowed USDC, and the borrowed USDC shares. Okay. Now, another thing that we're going to want to keep track of here is just the mint address of the USDC account. And the reason we want to do that is in the future, when we're passing through mint accounts for instructions, we want to be able to check if that mint account is either USDC or SOL. So if we keep track of one, we can just make a very simple if statement to check across the two. So we're going to store the USDC address, which is also a public key. Okay. We'll just want to keep track of when the account was last updated. So we'll just do last updated, and that'll be an I-64 because it's a timestamp. Okay. Now, the other account that we want to keep track of is the banks. So there'll be a bank for each asset on the lending protocol. And we want to initialize the bank and then keep a state for the bank. So let's define that account. Account, we'll use derive init space. We'll define the struct, and this is going to be a bank. Now, every bank should have an authority, and this authority is who will have special permissions to change the config of the bank. Okay? And then we want a mint address saved because that will be the mint address of the asset. Now we want to keep track of the total deposits in the bank. And then the total deposit shares. Now, since each user account can be liquidated, we want to keep track of the liquidation threshold, the liquidation bonus, the close factor, and the max LTV. Now, these are all constants needed to be able to calculate if an account is healthy or not. And these constants are usually created based on the volatility of an asset, so they're going to be asset-specific constants, so we're going to keep those in the bank of the asset. So we can do pub liquidation threshold. We'll do the liquidation bonus. We'll do the close factor. And we'll do the max LTV. So just to recap what all of these mean, the max LTV is the max percentage of collateral that can be borrowed for a specific asset. The liquidation close factor is the percentage of collateral that can be liquidated. You have the liquidation bonus, which is the percentage of the liquidation that's going to be sent to the liquidator as a bonus for processing the liquidation. And you have the liquidation threshold, which is the loan to value at which a loan is defined as under collateralized and can be liquidated. Okay, and then we'll also keep track of when this is last updated. Okay, so those are our accounts. Now we can start out with our instructions. So we're going to make a new folder inside the source folder and name this instructions. Okay. And because we're making a new folder, we'll have to make a mod.rs file inside of it. And then we want to update our librs to use instructions. Okay. And now we also need a mod file, back1 directory. So we'll do mod rs. So far we've created a state file and we've created the instructions folder. Okay. Now we can start with our first instruction. So let's first focus on writing the instructions for the admin of the entire lending protocol. So we'll make a new file inside instructions, and this will be titled admin. And this is just handling initializing new accounts needed. So we'll update our mod rs and make sure we have pub use admin and pub mod admin. Okay. So in our admin rs, we're going to use anchor. Now we're going to want to be able to initialize banks for each asset. So let's first define the struct needed for our context to create the instruction for initializing a bank. Let's write that out now. So we'll do derive accounts, define the struct, okay, so first we're going to pass through the signer. So that'll be an account that's mutable. And we'll do pub signer, and that will be the signer type. Okay. Now we want to pass through the mint of the asset for the bank. So one thing to note here, we're saying for simplicity SOL and USDC. However, typically for lending protocols like this, to make everything adhere to one type of token, they're going to be using wrapped SOL, because wrapped SOL is going to be an SPL token. So instead of having to handle anything with LAN ports and the system account, we're going to make sure all of the mint accounts are going to be an interface account for these banks. So we'll define mint, and this will be an interface account. And then mints. And now one thing that we haven't done yet is adding the SPL token to our cargo toml. So let's go to our terminal. We're going to do cargo add anchor SPL. Okay. We'll just check the version here. So we'll go to cargo toml, and we have 30.1. Okay. So going back to admin, we're going to want to import mint, and the mint is going to come from the token interface. Now we're going to want to initialize our bank. So we'll set the account, and we're going to use the init constraint to initialize. And then whenever we're doing that, we need to pass through a pair. That will be the signer. We need to define how much space it's going to take up on chain. So we'll use the 8 discriminator plus bank init space. We're missing a comma up here, so let's add that. And then we're going to make the bank a PDA, so let's define the seeds. In the seeds for the bank, we're just going to use the mint key, because every bank is going to have a unique mint key for the asset that correlates to the bank. So seeds, we're just going to take the mint key as ref, and then we need the bump. Then we'll define this account. Okay. Now we want to import bank. So we're going to use crate for bank. Okay. And now this is having an error because we're initializing a new account and we need to pass the system program through, which we'll do that at the end. So we have the bank, and the bank is holding the information to the state of the account, but now we also need a token account to hold the tokens for the bank. So we're going to make one more account, and this is going to initialize a token account for the bank. So we'll use the account constraint. We're going to initialize, and we're going to set that this is for tokens we're going to take the mint of the mint account that we're passing through, and then we want to set the authority to itself. So token authority, and that is going to be the bank token account, which is what we're going to name this account. And then we need a payer, which is the signer. And then we'll need the seeds for this account. So we don't want to use an associated token account here. We want to just have a token account with a PDA. So we're able to know that this account is specific to the lending protocol bank. Okay, so we're going to name this Treasury. And then we're going to take the mint key as well. And then since we have the seeds, we need the bump. And then we'll name this the bank token account. And this is going to be an interface account since we're using the token interface. Okay. Now, lastly, we need to pass through two more accounts. One is going to be the token program because we're creating new token accounts. And that will be an interface. For token interface. And then lastly is the system program. Okay, so now our error with bank went away because we're passing the system program through. And now we just need to import both the token account and the token interface. And these should both come from Anchor SPL token interface. There we go. And now that's updated. So this is everything we'll need for the struct to initialize new banks. So let's write the instruction for that. We're going to process a init bank. And that will be the context. And we'll pass through the context struct that we just created, which is a init bank. Okay, we'll return a result. Now the initialization happened in the struct. So all we're going to do here for the function is just saving the information we need to the account state for the bank. So let's load in the bank. We'll take a mutable reference of the account, and then we're going to update the mint address. And this is going to be the context accounts.mint.key. Now we're going to take the authority, and that's just going to be the signer. And then the liquidation threshold, we're going to have to pass as an argument here. So we're going to update to add in liquidation threshold. That will be a U64. And let's update bank liquidation threshold. Okay. And then let's also update the max LTV. And we'll add this as a parameter as well. Okay, and then we can just return OK. Now that we have this function, we can take this to our librs and declare our first instruction in the program. So here we go. We're going to init bank. We're going to take the context for init bank, pass through the liquidation threshold and max LTV, and then use the process init bank function that we just created in our previous file. Now we'll go back to the admin file, and there's one more account that needs to be created, and that is the user accounts. So let's first create our struct for that. We'll do derive accounts, and we'll do pub structs. This is going to be for init user. And first we're going to pass through the signer. And then next we're going to pass through the user account that we want to create. So accounts, and we're going to initialize here. So we'll use the init constraint. We'll have the payer as the signer. The space we'll calculate with init space. The seeds, we're just going to have the signer key. And then the bump. Okay. And then we'll just name this account as user account. And then because we're initializing a new account, we need to pass through the system program. Okay. And now we'll just update our crate to use user. One more thing to do in our admin file is to create the function for process init user. And the context is going to be the init user struct we just created. And then we're also going to want to pass through the USDC address, just because we're going to be doing that check throughout this entire program. So we want to just keep track of what that is. So this is another challenge, is how to optimize, how to keep track and check what mint address you're using, and you'll understand why we need this as we start to write out the logic. So we're going to load in the user accounts. We're going to set the owner as the signer key, and then the USDC address as the USDC address public key that was just passed through. Now we can take this function and pull it into our librs, and we're going to make an init user. There we go. So that's everything we need for the admin side of things. Now let's write our instruction to deposit. So whenever you use a lending protocol, the first thing you want to do is deposit an asset onto the protocol, so you now have collateral that you can borrow against. So let's write the instruction to allow a user to deposit an asset into its respective bank. So in our instructions, we're going to make a new file, and that's going to be our deposit.rs. Okay. Now we want to immediately go to the mod.rs file and update that. So we'll use deposit and then mod deposit. Okay. We'll go back to deposit.rs and we're going to use anchor. Now, let's define our struct for the context for the deposit instruction. So let's think about all the accounts that are needed for a user to be able to make a deposit into the protocol. So the very first thing is the signer. That's going to be the signer of the instruction for the deposit instruction. So we'll do derive accounts. We're going to do pub structs deposit. Okay, and the next thing we're going to need is the mint account for the token that we're trying to deposit. So we'll add in pub mint, and this is going to be an interface account. Now we're going to need the bank, which is what is going to have all of the information related to the bank that we want to deposit into. So let's load that. And this is going to be mutable because we're going to be updating the state in the bank. And we'll need the seeds as how we've defined it when we initialized the bank, which was just using the mint key. So we'll use the mint key, and then because we're defining the seeds, we need the bump. Okay. And we'll set the bank is going to be an account, info bank. Okay. And now when you deposit a token into a bank, that token is going to be sent to the bank token account. So we're going to need the bank token account as well. And this is going to be mutable because we're depositing into the account. And then the bank token account, we set those seeds as the treasury and the mint key. So treasury let's just double check to make sure we have our seeds correct. So treasury and the mint key. Okay. And then we need to update our imports. So we need the mint from the SPL token interface, and we need the bank from the crate. Okay. And now because we passed through their seeds, we need our bump. Okay. And this is the bank token account, which is an interface account and token account. There you go. And now we're also going to have to import this from the token interface. Okay, so the next account we need is the user account, and this is what is storing all the information for this specific user who is using the lending protocol. So we'll pass through account, set it to immutable. We're going to define the seeds, and that is just the signer key, and then the bump. Okay. And then we'll define this account. And we need to make sure we import user from our state. So we have the bank that has the state for the bank. We have the bank token account that is holding the tokens for the bank. We have the user account that is the state for the user. Now we need a user token account that's going to take the tokens that we're depositing and transfer into the bank token account. So we're going to set the user token account. Now this will be an associated token account of the mint address of the token that they're depositing into the bank account. So we're going to load in the associated token account for this mint address for the user. So we need the associated token. And that will be the mint account that we passed through up here. And then we'll do the authority. Is the signer. And then we need the token program. And then we'll just label this account for the user token account. And this is an interface account and a token account. There we go. And then we'll need to update our imports, which token account already exists, so we're good. Now we need to pass through the token program, associated token program, and the system program. So pub token program, that is an interface, token interface. Now we need the system program, and we also need the associated token program. Okay. And then we'll update our imports, all coming from token interface. And this one is going to be coming from the associated token. So that is our struct for deposit. Now we can go ahead and write the logic to make a deposit into the protocol. So let's see, how are we going to actually deposit a token into the bank? We're going to want to make a CPI transfer from the user's token account into the bank's token account. Then we're going to want to calculate the new shares to be added to the bank and the new shares for the user. we're going to want to update the user's deposited amount and total collateral value, and then update the bank state as well. So let's start with making the CPI call. So pub fn process deposit, and this will be the context for deposit. And we want to specify how much the user is going to deposit into the bank. So we'll have amount. Okay, so we'll first need the transfer CPI accounts. So let transfer CPI accounts. And this is going to be a transfer checked. And then we want to make sure we have this as an import. And transfer checked is going to be coming from the token interface, which isn't showing up here, so we're just going to write it ourselves. Transfer checked, there we go. Now we need to pass through the from, mint, to, and authority fields. So first is from, and you're transferring the tokens from the user's token accounts. So we're going to do accounts, user token account to account info. And then up next is going to be to, and this is to the bank's token account. And then we need the authority, and the authority is going to be the signer of the instruction, because the signer owns the user's token account. And then lastly, we need the mint, and that is the mint account that we pass through in our struct. Okay, so there's our transfer. Now we need to define the CPI program that's going to be used. And since all of the tokens we're going to be transferring will be interface account tokens, we can use the token program. So let CPI program ctx.accounts token program to account info. Okay. And now we're going to need the CPI context. So let CPI ctx equal, and we'll do CPI context new. And this will pass through the CPI program and the transfer CPI accounts. Okay. And now we need the decimals. So the decimals we can just get from the mint account. So ctx.counts.mint decimals. We don't need to unwrap that. We can just directly grab it. Now we can actually process the transfer. So we can do token interface transfer checked of the CPI context, the amount, and the decimals. And then we'll unwrap that. Okay. Now the transfer took place. So we transferred tokens from the user's token account into the bank's token account. Now we're going to have to update the state for both the user account and the bank account to reflect this transfer. So let's first load in the bank. Let bank equal, and we'll take a mutable reference to the account for bank. Now to be able to calculate the shares that we want to update in the bank state, we're going to have to do a little bit of dividing and multiplication. But we're going to have to do it a special way in Rust to take into consideration for overflow and underflow errors. We're going to be using the checked prefix for divide and multiply in Rust to be able to handle any errors that happen if there is an overflow or underflow error. So if there is an error, the checked divide and checked multiply is going to return either a value or a none, and it's not going to panic. Where if you just divided and it returned an error, it would panic. So we're going to set the deposit ratio which is what we need to calculate the shares for a user. So the actual formula for calculating the shares, it's going to be deposit shares is the total deposit shares times the deposit ratio. So we need to calculate the deposit ratio, which is the amount deposited divided by the total amount of bank deposits. We'll do let deposit ratio equal, and it's going to be the amount that we deposited, check divide by the bank dot total deposits, and we'll unwrap that. Okay. And now we're going to calculate the user shares. So the user shares is calculated by multiplying the total deposit shares by the deposit ratio. So we'll do bank dot total deposit shares, check to multiply by the deposit ratio, and unwrap. Now there's one bit of error handling we're going to want to add, and that is we don't want to divide by 0. So if there are 0 deposits, we're just going to want to handle that. So we'll do if the bank dot total deposits is equal to 0, then we'll return the total deposits is equal to the amount that was just deposited. So total deposits is equal to amount, and the total deposit shares is also equal to the amount. Okay, and one more thing, we need to go back up to the token interface and make sure we import. So now that we have the shares calculated, we also want to load in the user account. So we'll do let user equal, it will take a mutable reference to the user account. And now we're going to want to update the information for the user. So this is where we need to take in the USDC address that we saved the user state. So all we're going to do is have a match statement. So we'll do match, and we'll take the mint account that's being passed through in our struct. So accounts.mint.toAccountInfo, and we need to take the key of that. Okay. Now, we're going to delete what Copilot suggested because that's incorrect. So if the key is equal to the user's USDC address, then I'm going to want to update the user's account for deposited USDC. So user.deposited USDC now will be incremented by the amount that was just deposited. So amount. And we're also going to want to increment the shares. Okay. And then else, since it's only a 2-asset protocol, we're going to know that it would be SOL. So we'll update the deposited SOL for the user. Okay. And now let's just make that happy by returning an OK. Just skip ahead a bit. Now, one thing to take into consideration. Lending protocols usually take 2 options. When you deposit, they either mint a collateral token for you to represent the collateral that you have in the bank, or they create a share for you to represent the portion of the bank that you own. So in our case, we're going to be using shares instead of burning and minting tokens throughout the protocol. Now we just have to update the bank. So the total deposits are now going to increment by the amount, and the total deposit shares will increment by the user shares. So that is our deposit function. So now we can take this function and we can state it in our librs. So we'll add in pub fn. We're going to deposit. We'll take in the context for the deposit, the amount that we want to deposit, and we're going to use the process deposit function that we just stated in our previous file. Okay, so that is good to go for deposit. Now, if I deposit
you want to be able to also withdraw whatever asset you deposit into the bank. So let's create the function to be able to withdraw next. So in our instructions, we're going to add another file for withdrawal. Okay, now that we created the file, we want to update our mod. And mod withdrawal. Okay. Now in our withdrawal, we want to use anchor. Now let's define the struct needed for withdrawal. So once again, we start with derive accounts and then defining our struct, which will just be withdrawal. We'll first pass through the account for the signer. And we'll also pass through the mint account for the asset. And here we'll need to import the mint from token interface. Okay, now we need the account for the bank that's holding the state for the bank. So we're going to load the account, make it mutable because we'll be updating the state. We'll need to define the seeds for the account. And the seeds just come from the mint key. And then we need the bump. Okay. And then this is just the bank. And now we'll also have to update our import to have bank. Okay. And now we're withdrawing the asset from the bank token account. So the asset is currently being held in the bank token account and we want to be able to withdraw from it. So we need to pass through the bank token account as well. And the seeds for the bank token account, let's go back to where we defined this, right here. So it's just the treasury and the mint key. We'll copy that over. Okay. And this is just pub bank token account. Which is an interface account, token account. And now we want to update our import for the token account. And this should come from the token interface. Okay. Now we need the user. We need the user's account state, and we also need the user's associated token account for the mint. We'll do account. It should be mutable. We'll set the seeds. And the seeds for the user's account is just the signer. We need the bump. And then we need to define the account, which is the user account. Our state is going to be the user account we defined in our state file. So we want to update the import here to have the user. Okay. And now we need the user's token account that we're going to be withdrawing the asset to. We're going to do an account. And now when we're defining this account, the user should already have the associated token account because they deposited to the lending protocol. But just in case, because we can't guarantee that the user has this account, we're just going to use a init if needed here. And since we're using init if needed, we're going to have to update our cargo toml. So we'll go back here and we're going to do cargo add, and this is coming from anchorling. Yep. And we'll add the feature for a init if needed. Okay. And now you can see that feature was added to our cargo toml. Okay. So init if needed, if we have to initialize, we need the pair. Okay. And now for the associated token, We have the mint, which is the mint account that we already passed through. We have the authority, which is going to be the signer. And now we have the associated token program, which is just the token program. And then we have just to define this account. So the user token account. And this is going to be an interface account. Token account. Okay. And now we need the token program, which is an interface token interface. We need the associated token program and the system program. Okay. And now we just need to update our imports, and that is our struct for withdrawal. So we'll add the token interface, and we'll add the associated token. Now that we have the struct, we're going to be able to write the logic for our instruction. So let's define the instruction to process the withdrawal. So process withdrawal. And now we also want to allow the user to specify how much to withdraw. So we'll add that as an argument here. And we want the results. Okay. Now here with the withdrawal, it's going to be a little different than deposit because we're withdrawing tokens from the bank token account. And we want to make sure that the user has deposited enough tokens to be able to withdraw. They can't withdraw more tokens than they already deposited. So let's do a check for that first before we process the transfer of the tokens. So we'll first load in the user account because that will tell us how much the user has deposited. So we'll take a mutable reference to the account. And now we're going to check to see if this mint account is either USDC or SOL. So we'll do ctx.accounts.mint. And we're going to do toAccountInfo key. And we'll do not what Copilot suggested. Let's delete that. So if this is equal to the USDC address, then I'm going to set the deposited value equal to the deposited USDC. So let's go outside of this if statement and just define the deposited value. That is a U64 type. Okay. Now I will set the deposited value to the user's deposited USDC. And if it's not the USDC address, then I'm going to set the deposited value to the user's deposited SOL. Okay. And now, just to get rid of this error, we're going to jump ahead and return our OK. So now we can check if the amount is greater than the deposited value into the bank. So we'll do if amount is greater than deposited value, then I want to return an error. So we haven't written any custom errors yet within this project, so we're going to write our first custom error. So let's first go back and create a file for errors in our source folder. And we'll do error.rs. Okay. We're going to update our mod file. Okay. We'll update our lib.rs. We'll go here and we're going to use Anchor. And now we're going to use the error code from Anchor. And then define an error code enum. So we'll do pub enum error code. And then we'll write out our first error message. So in the withdrawal, we'll do return error. error code, and we'll just do insufficient funds because the user doesn't have enough funds deposited to withdraw the amount that they're requesting. Okay, and then we're going to copy this error we just wrote into our errors for our first custom error, and we'll define the message that we want. Okay, and now we need to use the error codes. So use create error code. There we go. And I think I spelled sufficient wrong, so let's fix that. Yep. There we go. And now we'll go back and fix the typo here. There we go. And here we have a type mismatch because we didn't pull the key. There we go. Okay. So now we have checked the amount of deposited funds from the user into a specified bank. And if it's an incorrect value, we're returning an error. But if not, now we can go ahead and process the transfer for the user to be able to withdraw funds from the bank. So this is going to be very similar to our transfer from deposit. So we'll do let transfer CPI accounts. Okay. So we'll use transfer checked. We want to make sure we import that. And it's not suggesting the right import, so we'll go and manually import. It should come from the token interface. So we'll do transfer checked. There we go. Now let's see, transfer check does from mint to an authority. So from, it's coming from the bank token account because we're withdrawing from the bank. It's going to the user's token account because the user is withdrawing to themselves. The authority is going to be not the signer here. So it's actually going to be the bank token account. Because when we initialized the bank token account, we made the authority itself. So we can just set the authority to the bank token account. Okay, and then the mint is the account's mint to account info. Okay, great. So that is our transfer CPI accounts. Now we need to set up our CPI program, which is just going to be the token program because we're transferring tokens. So let CPI program be the token program. Now let's think about this transfer. It's a little bit different than the previous transfer because we're transferring from the bank token account, which is its own PDA. So whenever you want to make a transfer with a PDA, the PDA has to sign for it, and we're going to have to derive the signer seeds. So let's first define what the signer seeds are for the bank token account, and then we're going to be able to process the transfer. Let's do let signer seeds. Now this is 3 references, so 1, 2, 3, and a U8. And this is equal to, we have 1 reference, and then we have another reference, and this is where we defined the treasury for the bank token account. And then we also had the mint key as part of the seeds. And then we'll need to include the bump. And then we need to define what the mint key is. So let the mint key be ctx.accounts.mint.key. Okay, so there is our signer seeds. Now we can create the CPI context. So let CPI ctx equal, and we'll do CPI context new. And this will be for the CPI program and transfer CPI accounts. And we're going to use with signer this time and add in the signer seeds, which update the formatting here. Okay, there you go. Now we need the decimals, and that can just be pulled from the Mint account. And then we can actually process the transfer. So we'll do token interface, transfer checked, the CPI context, the amount, and the decimals. Now I want to make sure the token interface is imported. Okay. So now that we've processed the transfer for a user to be able to withdraw tokens into their own token account, we want to update the state of both the user and the bank to reflect this token transfer. So we're going to first load in the bank. We'll take a mutable reference to the bank. I now need to calculate the shares to remove. So when we calculate the shares to remove, we're going to take the amount divided by the total deposits in the bank and then multiply that by the total deposit shares. So we're going to do amounts. We'll cast as an F64 divided by bank dot total deposits, also cast as an F64, and then we'll multiply that by the total deposit shares. Okay, now we want to load in the user account. And then we're going to do the same thing we did earlier by updating the users deposited either SOL or USDC by checking the Mint address that's being passed through. So we'll do if ctx.accounts.mint to account info and get the key. If this is equal to the user's USDC address, so we're going to decrement the deposited USDC by the amount that is being withdrawn. And we're going to decrement by the shares to remove. And then else, we're going to do the same thing, but for SOL. Okay. And looks like I had a typo in the users deposited USDC. Okay. We'll have to fix that. All right. And now all we have left is just to update the bank state. So the bank's total deposits are going to decrement by the amount. And the bank's total deposit shares are going to decrement by the shares to remove. So now just recapping the logic here, we're checking to make sure that the user is withdrawing assets that they have already deposited. If they're trying to withdraw too much, we're returning an error. If they're withdrawing an amount that is accurate, we're going to process the CPI transfer from the bank token account into the user's token account. And then after that, we just update the state for both the bank and the user to reflect the transfer that took place. So we deposited and we withdrew. Now we can just go back to our librs and add in the withdrawal function. So this is just pubfn withdrawal. It's going to take the context withdrawal, the amount, and then we're going to process withdrawal, which is the function we just wrote in our previous file. Okay. So far, a user is able to deposit assets into a specific bank and then be able to withdraw those assets. But now we want to allow a user to be able to borrow another asset. So when they're borrowing an asset, they're using the deposited assets as collateral. So we're going to calculate the collateral that a user has to find out how much that they're able to borrow against the collateral that they deposited into the bank. So let's write our instruction for borrow. So we're going to add another instruction file, and that will be borrow.rs. And we'll use anchor here. Okay, we're going to update our mod file. So pub use borrow and mod borrow. Now let's start by defining the struct for our context. So we're going to use derive accounts. And the struct is going to be for borrow. We'll use the lifetime specifier. And now let's start with the account for signing the instruction. So the first account we're going to pass through is going to be the signer. And we'll also need the mint, which is the mint account of the token that the user wants to borrow. And that will be an interface account. And now we'll have to update our import mint, and that is going to come from the token interface. And there is a weird import that came in, so let's actually delete that and re-import mint. Okay, there we go. All right, next we're going to need both the bank of the mint that the user wants to borrow and the bank token account of that mint as well. So let's pass both of those accounts through. So we'll do, okay, there we go. So Copilot was able to guess it pretty well. We're loading in the account, we're taking the seeds of the mint address, and we're using the bank, and we need to import that from our state. Okay, next is going to be the bank token account. So account, this is also going to be mutable. The bank token account will go back to admin. This one I always forget. So it's just treasury and then the mint key. So now we can paste that in. And then we need our bump. Okay. And then pub bank token account, it is an interface account, token account. We're going to import the token account, and that should come from the SPL token interface. There we go. So next we need the user's account from the protocol. So we'll do account. This is going to be mutable because we're going to be changing the account state. We need the seeds for the user account, which is just the signer key, and then the bump. Okay. And then we'll just define this account, which is just the user account. And now we're going to have to import user from the state. Now we're going to need the user's token account for the token that they're looking to borrow. We're going to have to use a init if needed here for the token account because the user is borrowing a new token and you don't know if they have already created their token account for this token. So we'll do account, and we'll do a init if needed. The payer is the signer. We're doing an associated token account, and we'll use the mint of the mint account we passed through, the authority, which is the signer, and then the token program, which we will pass through after this. So now we'll just name this as the user's token account. It's going to be an interface account, token account. Okay. So now we need the token program because we just referenced it here. We're also going to need the associated token program. Okay. And lastly, we need the system program because we're potentially initializing a new account. And then we just need to update our imports. So token interface should be from the SPL token and then the associated token. Okay. Now our imports are updated. So that is everything we need for the account struct to process our borrow instruction. Now we can start writing the logic for borrow. So let's go down here and write pub fn process borrow. We want to pass through our context as the first argument, and that will be the context of the struct we just wrote above, which is borrow. Okay, now we want the user to specify the amount that they want to borrow, so we'll add that as the next argument, which will be a U64 type. will return our result. Okay, so now we have the basic functionality of a withdrawal function. And just to recap what we have, there is the deposited value is calculated. We're checking to make sure that the amount that the user is requesting to withdraw is less than or equal to the deposited value into the bank. And then we're taking the CPI transfer from the bank token account into the user's token account to withdraw their assets, and then updating the state for both the bank and the user. However, there's one critical part that's missing here, and that is being able to calculate interest. So when you're using a lending protocol, the main benefit of a user wanting to deposit their funds into the protocol is because they're earning an interest by depositing the funds. So whenever a user is borrowing the funds, they're paying an APY on the funds to be able to borrow that asset. So we need to take into consideration the interest calculation when we're actually doing the check for how much a user can withdraw. Because if they deposited funds, they're going to have a slightly larger value of funds held in the bank than they originally deposited. So we can adjust our check for that. Now let's go back and figure out how we're going to integrate our interest rate. Typically, in most lending protocols, you're going to have a dynamic interest rate. So one challenge for you if you're working on optimizing this code base is how are you going to integrate a dynamic interest rate? For simplicity here, we're just going to have a fixed APY on all of the banks to be able to calculate. But for further optimization, you would want to integrate a dynamic interest rate. So let's first start by updating this check between the amount and the deposited value. So we now know that the deposited value is going to be larger than the original calculated deposited value. So let's get rid of this check. And let's start to calculate our interest rate. So first we need to make sure that we're logging when the user deposited their funds. So we're going to go back to our deposit function. And at the very end of the deposit function, we're going to now use the last updated field that we originally put into the user state. So we'll do user.lastUpdated is equal to, and we'll do clock.get the current Unix timestamp. So now we're keeping track of the time the user deposited into the bank. Now we'll go back to the withdrawal function, and we're going to be able to calculate the time difference. So we can just do let the time difference equal, we'll load in the user's last updated, and subtract by the current time. Okay, now we have the time difference. So up next is the interest rate. And since we're going to simplify things and have a fixed interest rate for each bank, we can go back to our bank state and just set a fixed interest. So we'll go to the state, bank, and we'll add in interest rate. And then at the time that we initialize the bank, we're going to set the interest rate to 5%. Okay. Now going back to withdrawal, we can now calculate the new total deposits into the bank with the accumulated interest rate. So we'll do bank.total deposits is equal to, and we haven't loaded the bank in yet, so let's first load that in. We'll do let bank is equal to a mutable reference to the bank, Now, the formula for a compound interest over a specified period of time, it's going to be the original value times the natural log to the power of the interest rate times the time that has elapsed. So we're going to calculate that here. We'll do bank.total deposits. We'll cast as an F64 for the calculation, times, and we'll need E dot to the power of, and we'll take the interest rate. So we'll do bank dot interest rate, cast as an F64, times the time diff, also cast as an F64, and then we'll want the entire calculation cast back as a U64 to be in the same type for the total deposits. Okay, so that is now our total deposits in the bank, taking into consideration the APY on the bank. Now we can calculate the current value of one share. So we'll do let's value per share equal, and we'll do the total deposits from the bank divided by the total deposit shares. Okay. And now going back to our previous calculation, we do have to import E. So that just comes from the standard constants within Rust. And one thing to update here is that to use E to the power calculation, we're going to have to use an F32 type. So we'll just recast as an F32. Okay, there we go. Now that we have the value per share, we're going to want to calculate the user's value. So we'll be able to take the user's amount of shares and calculate their entire deposit value. So let user value equal, and we'll do the deposited value divided by the value per share. Okay, so now we have the entire user value taking into consideration their accumulated interest from the bank. We can now do our check to make sure that the amount that they're requesting to withdraw is accurate. So we'll do if, and this time we're going to take the user value. If the user value is less than the amount then we'll return the error for insufficient funds. So now a user can deposit and withdraw from a bank. Now we need to allow a user to be able to borrow against their collateral. So the next instruction we're going to write is borrow. So let's get everything ready to write our borrow instruction. We'll create a new file for borrow rs, and then update our mod file. Okay, and now we'll go back to our borrow file. We're going to use anchor. So now we have our borrow. And we're going to start by setting up our struct of all the accounts that we need to pass through to run the instruction. So we'll start with derive accounts. Okay. And we'll name the struct borrow. Okay, so the first account we're going to pass through is our signer. That is who is going to be signing the instruction to call the borrow function. Okay. So Copilot made some suggestions. Let's see what they did. So we need the mint. Yes, so the mint is the interface account. And we're going to import the mint. And that's coming from token interface. Okay, we'll also need to pass through the bank. The seeds for the bank is the mint key. and then we're going to import the bank from the state crate. And then next is the bank token account. So we have both the bank that's holding the state for the bank, and we have the bank token account that's holding the tokens for the bank. And now we'll import the token account. Also coming from token interface. Okay, and then the user account we need to hold all of the user state. This is where we'll be able to query how much collateral the user has deposited into the bank. And here we go. So this is what we're going to change from what Copilot suggested. So up next, we need to have a token account for the mint that the user is requesting to borrow, for the user to be able to accept that token. Now, we're not sure if the user has the token account or not because they're borrowing it, so they may not have the asset already. So we're going to have to use init if needed to be able to initialize, if needed, for the user a new token account for the mint that they specified. So let's do account. The first constraint is going to be init if needed. Okay, and because we're initializing, we'll need the payer. And then we're just going to specify that this is an associated token. And the mint is going to be the mint that we pass through up here. Okay. And then we need the authority, which is going to be the signer of the instruction. And then we need the token program. So we'll do associated token program. Okay. Now we'll just define this struct, and it will be user token account. And that's an interface account, token account. Okay. Now we're having some errors, and that's because we have yet to pass through the token program. We're also initializing a new account on chain, so we have to pass through the system program as well. But before we do that, there's one account that we need to pass through, and that is going to be the price update account. So to be able to borrow, we're borrowing a different asset than the asset we have as collateral. So we need to understand the value of the asset we have as collateral in USD to be able to compare it to the asset we want to borrow. And we need to get that by using an oracle. So we're going to use the Pyth oracle and get the real-time price of the asset we have as collateral. So to do that, we have to pass through the price update account from Pyth. So we'll do price update. And this is an account. And we're going to use price update v2. Now we need to get Pyth in our cargo toml. So we'll go to cargo add, and it's going to be the Pyth Solana receiver. So cargo Pyth Solana receiver SDK. Okay. So now we've updated our cargo with the Pyth Solana receiver. Now we'll go back to borrow, and we want to import the price update from Pyth. Okay. We now want to pass through the token program, associated token program, and system program as our accounts. So token program is going to be an interface, token interface. We need the associated, we'll do the system program since that popped up. And now we need the associated token program. And that is an associated token. Okay, so now let's update our imports. So we need token interface, we'll import from the token interface. And then associated token comes from associated token. Okay, now our imports are updated. And these are all of the accounts. We have a typo there, let's get rid of that. Okay, and these are all the accounts we'll need for the borrow instruction. So now we can start writing our logic for borrow. So pub fn, we're going to process borrow. And we'll use our borrow struct for our context that we just defined. And now we want to allow the user to specify the amount that they want to borrow. So we'll pass that through as an argument. That'll be a U64 type. Okay. So now I'm just going to return our okay at the end so we don't have a bunch of errors as we're writing everything. Okay,